Okay, good. So we'll put in all our class recordings. We'll also put in, slides, notes, and stuff like that, or anything we can sort of post. Uh, we'll put on the website. Right. All announcements, all discussion will be through Piazza. So announcements and discussions. Just because we can't really store stuff in Piazza. So we'll have all the links in Piazza, but the actual material will be housed, on the website. So having said that, hopefully you guys can glance at both these two main resources to see, at least how we plan to proceed with the class. And at the same time, definitely, we're going to build on a lot of material, right? So the later parts of the course will be dependent on the first parts and so on. So we sort of want you guys to understand, yeah, the materials as we go along. It's very hard actually to fall behind with the volume of the materials, right? So just try to keep that in mind, especially when it's online, right? So there's a certain amount of time management being left to the students, right? So it sort of is going to be, you know additional burden on you guys. Yeah. Yeah. So depending on what you sort of so let's just do it this way. So this is cross-listed as E220, and for UP students, ECE COE 197, right? So that means grad students are taking E220 while undergrads are taking the 197. The lectures are pretty much going to be the same, but for grad students, you get additional work, right? So for those enrolled in the grad course, you get additional work, a bit more, not really that much, but you do get some more requirements than the undergrads. Um, and so in this particular case, grading for UP students will be, uh, we're going to have the activities, and then our projects. But again, the undergrads and grads will have slightly different requirements. Okay? So I sort of was referring to EP because this is again part of the CIDR, the Center for Integrated Circuits and Devices Research. And one of the components of this is a DOST funded project. And one of the components of CIDR is try to promote IC design, right? To schools, companies, and so on. So this class is actually a first because we have, not only people from UP, but from various universities, companies, and some government institutions, right? So right now we have 68 attendees, I think. So we should have we have space for more, right? So the limit for this particular Zoom thing is something like 500. So if know someone or a classmate was not able to attend now, they definitely are welcome to attend in the future. Okay, so again, as you probably saw, registering to the Zoom links. So the Zoom lectures are going to be 7 to 8:30 a.m. Mondays and Tuesdays. But you have to register so that we sort of can keep track of all of these things. We have to report to the OST at some point. But it's also good record keeping. So if you have not, I guess you're here, so you've registered. But if you have classmates or someone else that want to attend, they have to register first. You have to just register once, and uh, so to get that link, and then that's good for the whole semester. Okay. Now, aside from these things, so we have our website, Piazza, our lectures. I'll be giving the lectures. We also have a complement of additional lecturers and teaching assistants or graduate assistants that will help us in the course. So we have 4 uh, graduate assistants and instructors who will help with the answering of our questions in Piazza. Right? So this should be hopefully a very fun semester. So we have lots of discussions. And again, yeah, you guys are encouraged to participate, right? So hopefully, the ideas that we talk about in class spur new ideas, spur new types of thinking, or at least extending what you've learned. And then we can talk about that, right? So, something along the lines of, okay, yeah, this thing is interesting. Can I apply it here? Or I sort of did not understand this particular concept very well, or I have, this looks like it's not intuitive, or it goes against something I've known before and stuff like that. We want to hear from that. We want to hear that from you, and then we can start discussions on that, right? So as much as possible, we want to clarify some of the concepts, or even some details that, like, okay, this is valid for only a certain thing, but there could be cases where the optimization is not valid at all, and then we can talk about that, right? Or if you're a grad student and you have your own research, so you're doing your thesis and you sort of want to apply it to this, you want some concepts in class to be applied to your thesis, then definitely we want to talk about that, right? So we want to start doing that grad thing, right? So hopefully, just to illustrate the difference between the grad versus undergrad, right? Uh, so mostly when you're in undergrad, you're in this information absorption, right? So you want to absorb as much information as you can. But sort of, again, grad is different. You're looking at the information generation. You're starting to figure out, okay, yeah, there's something that I can do here, some interesting thing that I can explore, and I add to the knowledge, right? So, but again, both of them obviously have to do with the material and the ideas in class, right? So definitely, those are the things that we are very excited about, and those are the things that we want to talk about in our discussions. But definitely, uh, again, like that cliche, there's no wrong question, right? So everything is interesting, and again, we're here to make sure you understand, right? We're here to help. Everyone is here to help. So please take advantage of this tool. Okay. Okay. So in this particular case, since we do have a bunch of people, uh, you guys can have a Q&A option in Zoom, or you can just raise your hand and so on if you have questions, right? And then we'll hopefully see that and try to answer all those questions as best we can. Okay, so if there are no questions, so again, a lot of these things are going to be in our website and in our Piazza. So individual grading, so for grading for other schools and companies, would depend on your instructors there, right? So they're going to come up with the metrics and how you're going to be graded. Okay, so if there are no questions there, then let's just jump right into the material in class. Okay. So first of all, what I want to talk about, this is E220, and the title is Analog Integrated Circuits. Right. So let's just try and uh, figure out the scope of this. So first of all, let's try to define what analog is. Right. So a lot of times, or at least for the purposes of this class, when we say analog, we sort of mean continuous variables in voltage, uh, continuous quantities in either voltage, current, charge, flux, and so on and so forth. Right? And analog is actually divided into, so hopefully we understand, right? So that means if you have over time, right, you have some voltage or current or, some waveform, the this thing is continuous, right? It exists for every point in voltage. Right? But it turns out that that is true for two additional classes, right? One, we have what we call continuous time. So under here, we have continuous time. That means the voltage is defined at all points in time. Right? So this is continuous and this is continuous. That's what we mean by analog continuous time. But in this class, we will also look at discrete time. That means it's still going to be continuous in voltage, current, charge, and whatever, but it's going to be only valid at certain points in time, right? So that means, okay, if it's discrete time, then it can only, maybe it's only valid at this point, only valid at this point, only valid at this point, right? So you have, let's say T1, T2, T3, right? So that still considers analog, and it turns out we sort of like that particular regime because it allows us a lot of optimizations, especially if your system is your analog system eventually uh, goes to an A to D and you convert it to digital, right? So just to illustrate that, okay, so if you have your analog input, let's say your analog signal, most of the stuff that we'll talk about will be analog processing, right? So the simplest analog processing that you can look at is an amplifier, right? So you can amplify, uh, but then you can think of other analog processing, right? You can filter, you can mix, you can up convert, down convert, you can multiply, and so on and so forth, right? Or you can change the frequency response, right? You can shift frequencies from one to the other, and so on. So it sort of is in continuous time. However, in most cases, right, so when you have a big system, it's always going to be advantages, or it depends on the system. You probably have an A to D here, right? So an ADC, and then you sort of get your digital signal, and then you go to a microprocessor at some point. Now, the ADC is something that, again, discretizes, right, the signal and removes some information. So ADCs are actually, you can think of that as two steps. One is you quantize in time. Uh, What does that mean? It means that if I have an analog signal, okay, so this is, let's say, V1 or VA, my analog signal, right? Some random signal, right? Uh, the first step, the first thing that an ADC does is to sample, right? So that means it quantizes in time, right? So you throw away all that information in between. And the second step is it quantizes in voltage. That means, okay, now I sort of divide this into, certain levels, like, okay, then you have one, let's say this many levels, then this becomes your least significant bit, and so on. So now, each of these things will be, you get the closest possible value for that, right? So because you only have, let's say, a limited number of bits at the output, right? But it turns out these two components can actually be separated, right? That means I can think of this ADC as just something that samples. That means it's a switch that samples in time, and a quantizer, right? Something that, for every input, I get certain levels only at the output. Right? So in a lot of situations, if you have this particular setup, you normally see that this is continuous time analog, this is discrete time analog, and this is going to be digital. Right? So when we talk about our quote unquote analog versus digital, we are sort of looking, the boundary is sort of somewhere here, right? And this, by thinking of it this way, we actually have a lot of opportunities to optimize. For example, if I have an amplifier up here, right, or a filter or something like that, if I know that I'm going to throw away this particular information, this particular part of the waveform, okay, my ADC will just throw it away. I'd rather not spend power or effort trying to amplify or filter that. Okay? So what people do is, instead of putting the processing here, you put the processing after the sampling, right? So that's not that clear. So you can put the processing up here, let's say the amplifier, and you come up with discrete time analog circuits. And one very common class of discrete time analog circuits are what we call switch capacitor circuits. And that's something that we'll also look at, because it offers a lot of opportunities to save on energy and power. Yeah. So when we talk about, just to make it clear, when we talk about analog, we're talking about these two things, right? Continuous time and discrete time. Okay. Okay. So any questions there? Okay. Or you can save your questions for later, or write it down and we can talk about it in the end. Okay. But if you have this, again, burning question that you want to ask, then feel free to raise your hand. Okay, good. So far, I forgot to ask if the audio was okay, or if you guys can see the slides. So if there's something weird there, then let me know. Okay. Okay, good. Oh, I didn't know that. So the webinar, it turns out, gives me all these thumbs up. So I will see your raised hand. Okay, good. Okay. Now, one of the things that we want to also understand about 220 is, oops, I did not write out. Of course, this is analog IC design. So let's talk about that for a bit. When we say design. Am I running out of slides? Yes. So when we say design, let's talk about this. You sort of want to understand, okay, we are looking at design. So what is design? Well, for us in analog, the design is a design process where we start with specifications. Then from there, we sort of figure out our circuit, circuit topology, everything about the circuit. And then maybe you do layout, and then you implement that particular circuit, right? So just to distinguish it from versus analysis, right? So analysis is exactly the opposite, right? So when you do analysis, most of the time I start with layout and I try to figure out what that circuit does, and I try to figure out the performance of the circuit. Yeah. And in most cases, or in most undergrad classes, okay, you start out with the analysis part, right? So you're given a circuit and then you try to figure out how it works. But in design, it's totally different, right? I need something that works like this. What's the best possible circuit that we can have? Right? And one thing that we want to understand here is when we design, okay, the specifications normally would give you functionality. Okay? But in real world applications, functionality or basic or fundamental functionality is the easiest thing to achieve because you have a bunch of other metrics that you need to meet, and we'll talk about that when we get to our design. But just to illustrate, okay, maybe it has to work over a wider temperature range, or the noise should be less than a certain amount, or the offset should be within a certain range, or the power is below a certain limit, right? So a lot of times that's what we want to understand, because a lot of these specifications are not independent, right? So for example, you have specifications for power, but you also have specifications for noise, for example. If you want to decrease noise, right? Oops. If you want to decrease noise, we'll see that power starts to increase. And if you want to decrease power, noise starts to increase. So we get to see a lot of these trade-offs, and that's what we want to understand, right? So we want to build these circuits so that we get this optimal trade-off. We have, we understand that, okay, this is the best we can do for certain limitations, right? So that's what separates good engineers from very good engineers. So this means, okay, that we sort of want to really understand where those specifications came from. Yeah. Because it turns out that not all metrics are going to be equally weighted for your application, right? Sometimes you put more emphasis on power, sometimes you put more emphasis on noise or gain or speed and stuff like that. So you have to understand these specifications. And for certain circuits, right, if you combine that with circuit topologies, then some metrics could be easier to achieve than others, right? So for example, you have an amplifier, right? And it depends on your amplifier topology or even the technology you're using. Sometimes it makes it easier to increase the power than to reduce the noise, right? So there are certain constraints that uh, you want to understand. Oh, what is that? So there's something blocking the screen. Let's see if I can. How do I do it? Does that work? Oh, okay, okay. How is that? Hopefully, yeah, got now. Okay, good. It turns out that, yeah. So I just figured out that. Oh, okay, it's still there. Uh, let's see if I. Now, okay, okay, good. Okay, so it turns out that if you have a bunch of windows open, even if your shared screen is sort of in front, screens at the back can actually block the view. Okay, good. Thanks. So yeah, so we're talking about all this, specs, and in some cases, right, the technology and the application can make it such that it's easier to do certain specs or to meet certain specs than others. Uh, and when we say easy, that means the cost is going to be lower. And when we talk about costs, it's not monetary cost most of the time. We'll see that we have different currencies in our design, right? And we'll see that the most common currency in analog design is gain, right? So if I have an amplifier with a lot of gain, I can use some of that gain to buy something else, right? So I can use gain to, let's say, buy bandwidth. I can use gain to buy better input and output impedances. I can use gain to get, lower noise. Yeah. Oh, when I say buy, that means if I reduce gain, okay, or I can trade off gain, I can increase bandwidth, I can improve impedances, I can improve noise, and so on and so forth. Right? And we'll see that this is interesting because now each spec can be, evaluated in terms of how much will it cost me, right? Which it turns out that means, okay, when I design an amplifier, how much gain am I targeting? When I design this amplifier, do I need a gain of 1 million or do I need just a gain of 10,000? Right? Because later on, I will have to sacrifice that gain to buy something else. Right? And that sort of also implies that when you understand the specs, right, where it came from, you can say, okay, maybe some things are easier to achieve than others, or some things might be impossible. So this is another thing that's important, right? We want to understand that the limitations of our circuits and limitations of the technology and stuff like that, to say that, yeah, this spec is impossible with this particular technology. Right? For example, fundamentally, if I have an ADC, okay, just a very quick example, you have an analog input and you have, let's say, n bits of digital output. And we'll see that what if I want to increase this to n plus 1, right? Theoretically, we'll see that there's a limit, right? If I want an ADC and I want to add one more bit, okay, it actually will cost me 4 times more power. Okay? Power increases by 4x. That is the minimum. You cannot go below this if you want to keep speed constant, right? So that means if someone asks you, okay, I have this 8-bit ADC and I want to convert it to a 9-bit ADC. I just need to add 1 bit, but I want to maintain the power and speed. You sort of can start thinking, yeah, that's not possible, right? So, and then you should be able to prove why that's not possible. So understanding the specs also allows us to understand the limits of what we can do with certain things. Okay? And these are fundamental limits, right? These are limits brought about by physics. So, and we'll definitely talk about that, right? It has to do with a lot with noise. Okay. So, given all of these things, right? What we want to do for this class is to somehow create something like a systematic approach. Right? So a lot of times you get ad hoc type design methodologies, but that does not scale, especially when your circuits become very complex, uh, and you get multiple specifications or metrics trading off, right? So we made an example of power and noise, but it's actually a more complex trade-off scheme, right? Power, noise, bandwidth, gain, and so on and so forth, linearity, and but yeah. So you want a systematic approach, but you want it to be based on fundamental principles. So fundamental, easy to verify principles, right? And by doing that, we can create approaches or methodologies for not only one specific thing, but for a wide variety of applications. Okay, so again, let me know. My handwriting is definitely very bad. So let me know if you guys, there's something we cannot understand in that screen. Right? So what we want at the end of the class is to try and apply this to, we have a project and we want to apply this to an amplifier. Let's say inside that ADC you have an amplifier. Yep. And we want to try and design something with a bit more realistic specs. Okay? And we're going to use a real design kit, right? So, and we'll talk about that in a bit. But in our website, we'll see that we'll be using, or in our activities, we'll be using open source tools, which is good. You don't have to use any of the fancy EDA tools, at least for this class. And we'll use a particular technology, the Sky 130 nanometer technology. So all our designs, all our activities will be using this particular design kit. So that means we'll be using transistor models from this process. And the good news is that you can actually tape out using this process, right? So the tools we'll use, the open source tools, as well as the design kit, will allow you to create chips, and you can have them sent out for fabrication. Okay. Okay. So having sort of outlined the overall theme for the course and how we sort of want to proceed, let's look a bit more into the analog world. So we said that, okay, we have this sort of classes of circuits. We have analog and digital. And we start to also see a lot more people using ADCs. Why? Because you sort of, again, this goes into something like a microprocessor or a controller or something digital. Okay. And why is that? Okay. Why are people, not doing 100% of the work in analog? Right? Just like we said, some things are easier to, some specs are easier to meet with different circuits, right? So if I use a digital circuit, some metrics or some specs are more inexpensive in digital, or some specs are easier to meet in digital, whereas some specs are easier to meet in analog, right? And one of the things that you also want to understand is, where do you draw the line, right? Where do you put that ADC, or where do you put that division between analog and digital? And that's something, at least from the analog side, we can say, okay, this is the cost of doing this thing in analog. And then when you take a digital class, you sort of understand, okay, this is the cost of doing things in digital. Then where do I draw the line, right, for my particular application? Now, that line has sort of been moving more and more, you know, encroaching in the analog side, and we are moving a lot more things into the digital side. Okay, and let's let's spend a few slides trying to understand why that is. Right? Okay. Again, if you guys have any questions here, let me know. So, one of the things that obviously is an ever-present, uh, you know, ever-present spec, or not even a spec, but it's the reason for doing a lot of integrated circuits, is cost, right? And the main motivator for all the advances obviously are cost. How do you reduce the cost of these circuits? Because that translates into more profit, right? So let's try to understand. Right? In digital, it's very straightforward, right? So if I build gates, I build a microprocessor and stuff like that, right? I have something like 1 million gates. Right? So how much is the cost of a gate? Or that translates to, what's the cost of a transistor? Right? And the reason why we sort of started to move a lot more things in digital is the cost per transistor is going down exponentially. Okay? Now, this is something like, if I'm not mistaken, a 2006 slide from Intel, or a figure from Intel, that is very optimistic. So they say, okay, they were in somewhere around the 22 nanometer type thing, or 30. Oops, change for it. When they tried to draw up this slide, and said, yeah, this sort of looks pretty neat. So what does this mean? If you do the slope here, cost per function decreases 29% per year. Cost per function. This is something that a metric the digital people use. Right? Goes down around 29% per year. So that means this is sort of people have already done these numbers. So the implication here is the cost goes down by 30x in 10 years. So this is also a reason why, okay, cost in 10 years, whatever I'm paying for now in terms of fabrication and so on, in 10 years it goes down 30x. So this is also one reason why we sort of try to avoid competing in cost. Why? Because, for example, Intel, if they do nothing but just scale, right? If they don't do any circuit design, they have one circuit design in something like 2000, and they do nothing except build new fabs that can manufacture those designs, their cost is going to go down 30 times in 10 years, 30x in 10 years. So if you want to compete with them, right, your circuits have to be better. Your for example, in terms of cost, your projection should be, my cost should be better than 30x in 10 years. It should be something like 100x reduction or 300x reduction, because they will get 30x doing nothing in terms of circuit design. Right? And if they add circuit design to this, they can actually get you, something like 100x or more reduction in 10 years. That means you sort of see this, right? So it's cost per function. So, but you're paying the same amount for a processor, but that just means you have more functions in your processor, right? So they can pack in a lot more functions and so on and so forth. But that's digital, right? But how does that compare to analog? So this is digital. Now, the problem with analog, let's try to compare. Okay? Cost per function is pretty much constant. So you might ask, if the cost of a transistor is going down, why won't analog circuits also follow the same trend as digital circuits? Okay. Because I'm probably still using the same transistors, right? So again, if you have something like a differential amplifier, if everything scales, the transistors should scale as well, right? So why won't it scale? What's going on? Why can't I, I'm just using something like, let's say 20 transistors here for a differential amplifier, right? The differential amplifier, 20 transistors, each transistor every year goes down, in cost. How come I can't take advantage of that as an analog designer? Okay. Well, it turns out fundamentals or physics also start limiting us. Right? And just an example, one limit would be noise. Okay? Specifically, SNR. And we'll talk about this in detail when we get to noise. But just to illustrate, the output noise of your circuit is dependent on what we call this KT over C noise, thermal noise. This is our thermal noise. So the output mean square voltage of thermal noise is KT over C. That this C is a load capacitance of your amplifier, right? So how much capacitance are you driving? And if I want to have very low noise, it turns out I need to have a relatively large capacitor there. But if I want to maintain speed, right? If I want to maintain speed, I need the same amount of current coming in. So even if scaling allows me to make smaller and smaller transistors, right? Scaling the dimensions allows me to make smaller and smaller transistors. It's not really a direct fit for analog, because noise tells me I need this much cap, and speed tells me I need this much current. Yeah. So that means that limits the amount, the size of your transistors. Right? I cannot build this thing smaller and smaller unless my current starts increasing faster than these things are decreasing. And we'll talk about that. Right? But ultimately, this is just one limitation. Another limitations we'll see is variations, right, and mismatch, which we'll talk about in a few minutes, right? But so a lot of times we'll see, people try to start encroaching or really want to put a lot of analog functions in digital, just because analog does not scale in terms of cost per function. Right? And it turns out that, okay, we'll talk about this also in a bit. There's a bunch of factors here. Okay? So does that mean why not just put all our efforts in creating better digital circuits to the point that we can just replace all analog circuits with digital. Right? So does that mean analog circuit design is going to die soon? Hold that thought, right? So let's try to understand what's going on now. Like I said, this is a relatively old Intel slide, right? So this is what they forecast going beyond 28 nanometers. But what's really happening now? A couple of, maybe a few years ago, not a few, maybe almost, wow, it's almost something like 6 years ago. Samsung, actually the same thing with Intel, looked at their fabs, looked at how much, what's the cost of a transistor in, let's say, a bit more modern era. So instead of cost per transistor, let's flip that metric and say, okay, if I have $1, how many transistors can I buy, right? And it turns out that, okay, yeah, when you go from something like 180 nanometers and stuff like that, transistor costs go down, and you get more bang for your buck, right? You get more transistors for your dollar. However, this is the interesting thing, right? It turns out that around 28 nanometers, and this is not only true for Samsung, but it's also true for Intel, this thing starts going down, right? Making smaller devices are now more expensive. I can't really say that, okay, yeah, as long as I keep scaling, I will get cheaper and cheaper transistors. But at some point, physics starts to kick in. Right? It's more difficult to build something like a 16 nanometer. More so the transition between a 20 nanometer and a 16 nanometer device is more expensive than transitioning from 180 to 130 nanometers. Right? So why is that? Okay. And we'll talk about this in detail when we get to our transistors. Okay. But I just want you guys to understand this overall idea, or at least where the field is going. So as soon as you start seeing something like this, where people are predicting now that 28 nanometers is where the optimal price per transistor is going to be, right? That's the technology node that will buy you the most number of transistors for $1. But yeah, that's interesting. But it sort of again goes against the original what we were talking about. As we move forward, this is probably not going to be true anymore. Right? The digital cost is not going down at a steady pace of 29% per year. So that's one. And another thing that I'd like to point out is, okay, why is it hard? Okay? Why is it harder to build these things? Aside from making everything small, obviously it's factored in, right? So when you go from 90 to 45 to 22, your clean rooms have to be better, your lithography have to be better, and so on and so forth. But that's sort of factored in these curves. But what changed when we start going below, right, 28 nanometers? Well, let's see how we normally progress. Let's look at how people are thinking about transistors. In our normal, planar device. So let's look at this. So we have our planar device, figure 1. If I look at the cross section, you get that very familiar source, drain, and gate, right? source, drain, and gate. Now, if you remember, the idea here is, okay, the gate produces electric field, okay, that sort of generates a channel over there. Okay, so the two things that are going to be interesting here is that, one, we know that the current is going to be dependent on that transistor length, right? The smaller the length, the larger your on current is going to be, which is good, right? Because to be able to get speed, you have a very large CL, for example, because you want low noise. I need a lot of current, right? So I get faster and faster devices, right? But that's good because when you start reducing the length, the current starts going up. Okay. Now, the problem is when that length becomes very small, it becomes harder and harder to turn the transistor off. Yeah? So that means even if I turn the transistor off, just because the source and drain are very close together, even if this is turned off, current can still flow, right? And you have a bunch of mechanisms there. One is leakage current, another is what we call sub-channel conduction. Ideally, you want all the current to flow next to that surface, but because they're so close together, right, you get conduction below that channel, right? So you can get leakage through there, or you can have breakdown. Okay? Just because of the fact that these things are very, very small, something like in the order of, sub 10 nanometer thing, right? So the issue here is, okay, I can actually make that current very large, but I lose control of the current, right? Because I can try to turn off the gate or I try to change the gate voltage, but it's not affecting the current that much anymore. So how do you move forward? Well, there's a bunch of ways, and one of the more common 28, 22 nanometer type devices are what we call the FinFETs. And as you can see, this is already, some people consider this like, 3D type device. So what you have here is you have this raised source and drain, right? So you can imagine the source and drain over here, right? And instead of having the gate control only one side, right? So the gate is controlling this side for a planar device. If I look at the cross section, what you get in a raised source and drain is that if I look at this in section, so this is the source, okay, the source pin, looking at it from this direction, okay, the gate is going around, right? So what does that mean? The gate controls three sides of that source, right? So it allows me to control the current coming in way better. Yeah. And obviously the trend now, people are sort of really are excited about, okay, if I can do that FinFET, I can extend that to what we call gate all around. Okay, so now looking at the source in this direction, I have the source and the gate seems, going all around so that the gate actually controls four sides of that source, right? So it controls the whole channel. So imagine that channel, but but over here it's controlling this, this, and this. So you actually have less chance of leakage and breakdown. I can start increasing the current, but at the same time maintaining control of the current. Yeah. And obviously, if I can do that for three sides, you can imagine I can do that for four sides. Right? I can control all that channel region over there, and to the point that maybe I can control all of that. Right? So it allows me to again do scaling. increase that current while reducing this leakage. This is something called the I-on to I-off ratio. Right? This is a metric on how they design transistors. I want to be able to have a lot of current, but I also want to be able to turn it off. And it turns out that our planar traditional transistors have very bad I-on to I-off ratios. And when you get to 28 nanometers, okay, Intel has a nice 28 nanometer FinFET. TSMC also has a nice 28 nanometer FinFET. And you get significantly better at this. But notice that, yes, I can design smaller and smaller transistors. Right? So that means Samsung said this, right? We can design something like 3-4 nanometer transistors, but we cannot make it as cheap as something larger than 28 nanometers. Because lithography to build this, the manufacturing you need to build that is way different from the one you need to build this. Right? So this is a sort of something we want to understand. And having understood how this works, we want an analog design methodology that can scale, right? We want something. So what we want now is something we can use to design circuits, analog circuits, in the planar or in FinFETs or later on in gate-all-around. Right? So the methodologies that we look at sort of are going to be still applicable. Right? That's what we want. We want to have them applicable to all of these. So we're sort of prepared when we start changing technologies, right? So the good news is that what we want to do in this class is going to be agnostic of technology. Right? In any of these things, we look at fundamentals and design it for, using with that in mind. Okay, okay, good. So any questions there? All right. One other limitation on why we cannot scale, or analog circuits cannot scale as much as digital, is, again, it has to do with signal to noise ratio and how digital scales. So a lot of these fabrication facilities, a lot of the fabs, are optimized for digital. Okay? So what does that mean? When you're optimized for digital, I want to be able to optimize inverters, right? So yeah, so when you're a digital designer, I think for the most part you can reduce everything to the performance of an inverter, right? And one of the things that we sort of notice is that power, the power is proportional to the load capacitance supply voltage squared, right? So if you want to reduce the energy, or power, you definitely want to reduce VDD times switching frequency. Right? So the good news about digital is that the noise margins, or the margins, are very large, right? So again, it's a 0 or 1 or 0 or VDD, such that there's a very large margin there, right? So for digital, I can just go on and reduce supply voltage because I only am representing 1 bit, right? However, so that's what you see the trend here. Supply voltages went down drastically from 2000s to just short of that 90 nanometer node. And one of the reasons why is I really want to reduce power. Why is that? Because the main limitation for all our digital stuff is power. Our processors running at something like a few gigahertz consumes a lot of power. So how much power do our processors consume? Right? So let's just think about, let's just put everything in perspective, right? So if I have a microprocessor, like an Intel, one of the latest Intel chips, these things consume 200 watts, right? Because they are running at something like gigahertz type thing. But what's interesting is the supply voltages of these things are something like in the order of 1 volt, right? So at max current, the current coming in from your power, let's say regulator and stuff like that, is something in the order of like 200 amperes. And that's sort of hard because now you have to dissipate all of that heat. Okay, and one way to start reducing that power consumption, that means reducing the heat. So I don't want very big fans in my mobile phones. I start reducing supply voltage, right? This is a very powerful knob in digital. Okay, it's VDD squared. So reducing it by a small amount, I get large benefits in terms of power. Okay. So you get this. However, this also allowed us to have smaller and smaller gate oxides, right? So that means if I have a transistor, source, drain, and my gate, okay, to be able to scale everything. So if I want to scale my horizontal dimensions, it turns out I also have to scale my vertical dimension. So this is my oxide thickness. And in, let's say, a lot of the advanced technologies, this is measured in terms of angstrom. Okay? Again, fun fact, a lot of, for something like in the order of these 45 nanometer node, the thickness of those that oxide pre-high K thing is going to be something around 10 angstroms. Okay? And this is when they were using silicon dioxide. But the problem is silicon dioxide, the diameter of your silicon dioxide molecule is something in the order of 3 angstroms. So you're actually just talking about 3 atomic layers of silicon dioxide separating the gate from the source. And that means you cannot put very high voltages in the gate. So when you scale, you actually have to scale down the supplies. Okay? But something happened, right? Something allowed us to maintain the voltage here. And what's that? Okay, the use of high K dielectrics. So that means, again, this is the gate. It's coupled to the channel by your oxide capacitance. Okay? So if I want to control the gate, that the channel, that capacitance should be very high, right? And that's the reason why we make this very thin, so we get more capacitance. So I can control the gate better. However, I get all sorts of problems. That means my voltage has to be low and so on and so forth. I get tunneling, I get gate current. So what people, okay, let's just change that dielectric. Instead of using silicon dioxide, I'll use hafnium oxide. And if I use hafnium oxide, I get higher dielectric constants. I get the same capacitor for thicker gate oxides. And that means, okay, I get the same benefit, but I can still use higher voltages. Right? So you can see that over here, right? Same benefits, but I don't have to scale that voltage as quickly. But again, you're still scaling, right? You're still moving this down because you get incremental gains there. But what does that mean for analog? Well, analog, we sort of really are interested in what we call signal to noise ratio. Right? And this means that, okay, the noise I want to bring down, but the other component of that ratio is a signal. I want this to be relatively large. But that signal is proportional to my supply voltage. Right? It could be VDD, half of VDD, twice the VDD, but it's still going to be tied somehow to VDD. Right? And if I start reducing that, then my SNR also goes down. It makes analog design very hard. Okay? And just to illustrate that, this is a nice little picture from Rutenbar CMU, uh, it shows a few things, right? One is that the drive of technology is to bring down supply voltage because you get a lot of benefits in terms of digital, right? Uh, and say digital, okay, yeah, because it's 0 to 1, there's a lot of noise margins. However, in analog, you're actually packing in a lot of bits in a waveform, right? So you get 0 to VDD, right? If you have, let's say, you know, it's going to go to an 8-bit A to D later on, then I'm actually packing 8 bits there, right? Or 3 bits in this case, and then 8 bits. So that means, okay, I need to have a resolution, okay, of VDD over 2 to the number of bits, right? So that means, okay, I have to be accurate when you do analog processing, right? So if this goes into an 8-bit thing, then I have to be accurate to VDD over 256, right? It's even worse if I have something like a 10-bit A to D after, or I need 10-bit resolution after processing, and that means VDD over 2 to the 10 is VDD over 1024, right? So when you reduce this, you still need this much accuracy, right? And at some point, you get the noise floor. There's going to be a certain amount of device noise. So when we talk about noise, which we'll spend quite a bit of time on, we mean noise generated by your devices, right? Because your transistors generate noise. Your resistors also generate noise, right? So that means even without any input, your circuit is generating noise. So that's a big problem, right? If you have an amplifier and you're generating noise at the output, how do you know if that's noise generated by your device or your actual signal, right? And that's why signal to noise ratio is very important, right? That means my signal should be very much greater than my noise at the output, right? And we'll see where that comes from. But because of that, the voltage, reducing that supply voltage is very hard on an analog designer. But it also brings out the very best of the analog designers because we are now forced to think, right? I want the same specs. I want to be able to still build a Wi-Fi radio. Still want to build a nice, fiber optic or Bluetooth link and stuff like that, even if I'm using very, very low supply voltages. Right? So this is a challenge that we'll actually be facing, at least we understand, going through the course. Right? So any questions here? Now, in the last 15 minutes, I actually want to talk about another thing. So we talked about supply voltage and scaling. Just to introduce the, at least the color that we'll try to look at when we design our analog circuits, what influences our design? Well, one is scaling, and ultimately it means supply voltage. But the other, it turns out, has to do with how these things are manufactured. Because the transistors become smaller and smaller, right? Then defects actually become very critical. So if you have a very small transistor, or let's say if you have a large transistor, if I have a large transistor, let's say very large transistor, versus a very small transistor, right? Now, if I have a speck of dust this size, right? Well, maybe it lands here. I might still have a semi-operable transistor, but if that same dust lands here, then it shorts out a lot of the things. Then the transistor is done for, right? So we need people are trying to control, okay, these manufacturing steps. But it turns out they cannot control it very well, right? So what do we mean by they cannot control it very well? They have what we call variations. So let's look at this very simple and very interesting graph by Sherka Borkar way back in 2003. Borkar is, one of the famous Intel people in charge of technology there. And this shows variations. This is the same processor. They just measured all the processors that they fabricated in that particular technology, in that particular fab. And, the frequencies are varying quite a bit. Notice that I get something like 30% variation in frequency, but I get something like 20x variation in leakage. Now this is interesting. Why? Because it turns out that this is directly translatable to on-off current, right? Frequency, again, is the speed at which we can charge that capacitor, and that is dependent on the current, right? So it turns out that I have variations in on current versus off current. And there are several things that contribute to this variation. So I want to talk about variations, right? And these variations are brought about by manufacturing imperfections. Okay? We cannot build perfect transistors or identical transistors. Right? There's going to be some sort of variations. And why is that? So let's take a look at a typical MOSFET. Right? Now, one very important thing, source, drain, gate, one very important metric is threshold voltage. And we'll define threshold voltage because we'll see it's not that easy to define, or at least on the practical side. On the physics side, the definition of threshold voltage is very well defined. But on the practical side, one, it's very hard to measure, and two, it affects a lot of things. So what determines threshold voltage? Well, it's going to be dependent on the doping, okay, on the channel doping, right? So the way they do this is they build and you dope that channel, right? So you get exactly the threshold voltage you like. But because these things are very, very small, right, the channel lengths are very small. If you do the calculation, right, some of these things for a minimum size transistor, right, the number of dopants here is going to be something like 100 dopants. Yeah. Just for me to adjust that particular threshold voltage to, let's say, 0.5 volts or 0.4 volts and stuff like that. Now that is interesting because that means if I just lose one atom, I change the threshold voltage by 1%. And that's one atom. But we know this is actually a hard thing, right? Because how do you implant dopants there? Use diffusion, right? One way is use diffusion, or the other way is use, you can use ion implantation. But both are very, very uncertain, right? Because either diffusion, right? These things diffuse, so you could lose an atom, or if you do ion implantation, you shoot the ions inside using high energy, but then you sort of create damages, right? And then you sort of heat it up so to heal the damage, and then that sort of makes, okay, these things also diffuse. So if I lose an atom, that's a very big deal for both the current, right, and the leakage, both currents, right, on current and off current. And we'll see that in the off region of our transistor, right? So for the on region, that's our square law, or we'll see, saturation type device. But in the off region, this is in subthreshold. And in subthreshold, that behaves exponentially. It looks like a BJT. Okay? So since it's exponential, right? And that means variations are magnified exponentially. That's why you get a lot of variations on the leakage side for 30% variation on the current side. Now, this is interesting. So, how can I design circuits that, for example, my amplifier, I need to design an amplifier with a gain of 1, right? It's a buffer, plus minus 0.001%. Right? And this is a typical spec, right? Okay, I want an amplifier with a gain of 1 with, maximum variation of 0.001%. A very, very high precision amplifier. But the transistors you're going to use will have current variations in the plus minus 30% and leakage variations in the 20x. How do we do that? Right. So we'll talk. This is something that we'll also spend a bit of time in class. How to build good circuits even if your devices have lots of variations. Right? So why are our manufacturing processes having this trouble? Because as you'll see, we have this first activity. You look at the variations. It's posted on the website. I'll post it on Piazza as well. It's the way we do lithography, right? So again, the main step for fabrication is lithography. We use light. We use light to pattern the stuff on our circuits. However, if you look at the light that they're using, right, with the minimum feature size, you get this interesting thing, right? So they're using something like light with a wavelength of something like 436 nanometers. That's fine if you're trying to create devices with something like 2 microns, 1.5 microns, and so on and so forth. So as long as the device dimensions are larger than your light source wavelength, this looks like a straightforward lithography step. But the problem is getting light sources to follow, the minimum feature size turns out to be very hard. So at some point you cross over. You want to start building transistors smaller than the wavelength of your light source, right? Which is ridiculous, right? So as you can see here, all of these things, 130, 90, 65, 40, they're built using light sources with longer wavelengths than your device dimensions. So what does that mean? It looks like you're trying to paint a very thin line, let's say a 1-inch line, with a brush, right? You have a brush that is something like 4 inches wide. How do you actually do that? Okay? So this is where a lot of the fancy developments in lithography happen, right? Because it's, we've done this, right? So these things work, right? We can build 90 nanometers devices with light sources at 193 nanometers. Okay? And we do that very well. So this is an example, right? So you can do 45 nanometers very, very accurately. So this is the actual cross section of the device, where you build a device and you sort of cut it in, to expose source and drain and everything, right? And we'll talk about this in detail. And then you can also see how metallization works, right? So as you can see here, that's sort of impressive given that the light source is larger than this. And the way they do that is what they call optical pattern correction, right? So one, you can either change the shape, so you pre-distort the light, right? So as you can see here, you pre-distort that mask because if you don't do, you just do straightforward pattern thing on the mask, you sort of get because you're trying to paint that 1-inch line with a 4-inch brush, right? You get very bad results. However, if you do pattern correction, basically you do wave tracing and optical, it involves a lot of computation, right? Then you pre-distort that mask so you can actually get the line that you want. Now, this is this comes in several flavors, right? You have either just correcting the mask, or in some cases you correct the mask and do second exposures, right? And you take advantage of constructive or destructive interference of the light, right? But ultimately, because of the way we do this, we get a lot of variations, right? We cannot build a lot of these things exactly the same way. And at the same time, the light source, so if you have a wafer, right? And a lot of times the light source is a point source. So the light sort of goes this way and this way, right? And it passes through your mask. So in some portions of the chip, light actually travels at an angle, or the wafer, and some portions of the wafer, light travels directly vertically, and so anything in between there and there, you have different angles where the light hits. So you have very small variations in this, right? So again, a lot of research goes into how to build that light source. But as you would imagine, maybe you get 0.01 degree change in angle. But like we said, losing one atom in very, very small devices can result in a significant change in transistor characteristics, right? Okay, so it's almost time. So what we'll do is, first of all, any questions here? Right? Hopefully we understand the takeaway here is really trying to understand the implications of the process, so we know what we're up against, right? When we start designing, we still want to design the best possible circuits with very little variations, right? Because if you want to run the Wi-Fi, you have to meet the specs of the Wi-Fi standard. There's no leeway there, right? And we do that even if all of these devices are somewhat not ideal. Okay. Okay, good. So any questions here? So we'll stop here, and what we'll do next time is we'll just give a short review of what we've talked about, and we'll just look at some examples, right, of analog designs that we sort of are, I think, very interesting. Okay. Okay, so that's it. And reminder, look at the website. There's our first 2 activities posted. So it's nice to, start to look at that so we don't fall behind. And yeah, so I see someone raised your hand. Who raised it? Can you raise it again? I cannot see. Or you can type in the question in the chat. But yeah, or if definitely ask the question in Piazza. Yeah. But yeah, so since we're again running out of time, thank you very much for attending. Hopefully you guys enjoyed our first lecture. See you guys tomorrow. Okay. Okay. So bye, guys.